I'm going to be more general right away before I'm going to share this next method with you in more detail. Because I'm going to look at a method which is more general, where I could even compare more than two. I mean, it could be that I had 3 or 4 or 5 different groups. Maybe I had young females doing birth control pills, older females doing birth control pills, a control group of young women and a control group of older elderly, or whatever. I could have many different groups. I could have all sorts of groups. I could have 3 different treatments, or I could have many different things. Maybe I have a multi-group situation where I not only want to compare whether 2 proportions are the same, I want to compare. Now, if it's the poll thing, presidential poll, maybe you have not a gender-based investigation, maybe you have a race-based investigation. We have Latinos, we have Caucasians, we have Afro-Americans, we have Asians, and even more that I couldn't think of now. That would be something, these kind of investigations, the consultants, people for the US presidents will have such detailed investigations of the different subgroups. And you might want to compare different proportions there across such groupings, not only 2, maybe several groups. It's just to motivate that I think it makes good sense that we should be able to test such a hypothesis also, that many different proportions, in this case K could be 2. So it could also be the 2-group case that I'm going to handle now. But just we have to find a new method now, because the method that I gave you for 2 groups, where I directly compare the P1 and the P2, doesn't work when I have P1, P2, P3, P4, P5. Because how should I, there are many different such 2s. How should I compare 5 things at the same time, right? I cannot just take one thing and subtract another thing and then compare them. That's not possible. I have to come up with another alternative, and here it comes. Here is the general table showing that I have K different groups. So this could be birth control group, this could be non-birth control group, this could be a 3rd group, this could be the Kth group. Actually, the table is now sort of flipped, if we want to make the link directly to my birth control data table. Now I have the proportions in the columns rather than in the rows, but still, I have a number of proportions here. There could be different ends, that's okay, like in the birth control, in the 2-group example. First step is to compute what we could call the best guess of P if everything is okay, if the groups are really the same. And that would be to take the total amount of successes, which is our generic term. In our example, the success was a disease, but that's the terminology. We count the total number and divide by the total number of people in the study. That is sort of the common proportion, you could say, across all groups. The one that should represent all the groups in case they are really the same, right? It's the best guess of the joint proportion, just taking across everything. This is how many the proportion of diseases we have in our case. Here comes the story now. The thing is, it's a generalization of the idea I told you before the break, where we should start thinking about what could we expect, or what should we expect, if the null hypothesis is really true. Now, I compute, that is a repetition, I have the joint proportion across all groups. If the groups are really the same, in terms of, the underlying P, the populations are really the same, I would expect, if the data should match exactly with this assumption, I should have exactly this proportion of people being successes in all the groups, right? I should have the same proportion. And that's what I'm saying. I should take each individual number. Each individual, I have 167 in one group, I have 62 in another group, I have 200 in a 3rd group, I have 500 in a 4th group. But if the group should match with the hypothesis of them being the same, I should have the same proportion of successes. the same proportion of successes in all groups. That is what we should expect if the hypothesis is true. I compute the expected values of successes. Here I basically just spell it out. And then I compute, but that would also be given more or less directly. I then also have the expected number of failures. That would just be the opposite number, you could say. If 50 out of 100 is expected success, then the remaining 50 would be expected failures. I compute these numbers, and then I compare. Then I compare across, I should say here, I have the observed, and then I have the expected. And I have expected values for each of the 2 rows. It's the number of proportions, success, failure, so I have 2 rows in the table, and I have k columns, right, as I showed you in the slide before. So among all those 2 by k combinations, here, 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 tuk, 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 here, here. Among all of those, I have, of course, the observed from the original table. That's my observed data as they come. This many successes, this many failures observed in each group. Then I have the things I just computed. I compare those observed with the expected values in each group, right? And I do it this way. I square those differences, and I relate it to the expected values. Actually, this could be a bit sort of out of the blue here. That this, why should we do this way of comparing? I think I would like, before I show you the remaining slides, let's start doing it in this example with the birth control data here. The birth control data, as I showed you, look like this. So these are the OIJ. Please note now, I'm going to exemplify this procedure, a procedure that works for k groups. I'm going to exemplify it in the example where I only have 2 groups, because that's the easiest. I don't have to write so many things. But the thing that I'm going to show you could be used even though I had 10 groups like this, right? It's just, but I'm going to use the 2-group case as an example for easiness. Then I need to compute the expected values. That is, I need to compute the EIJ to find the difference between the hypothesis and the data. This is the data. Here I'm going to compute sort of hypothesis-enforced data, you could say, expected data. What should I? Well, I already, no, I didn't actually. What is the joint P? I have to compute that one. I have to compute the joint P. What was that? That would be, all in all, I had 58 deceased here with a disease. Not, I have a word problem there. 58 out of, I have it here also, 58 out of 224. What is this percentage? This percentage is around 26%. 26% of all the females in the study get the disease here. Now, if I should now look at the group of, at the birth control group, say, here I have, this one is N1, this one is N2, right? I have 57 females in this group. Again, the table is on row-wise now instead of column-wise. Sorry about that. Among the 57, how many should get the disease if the joint proportion of 26% applies to this group? Well, then this one, which we could call E11, should be the joint proportion times N1. This was my slide. This was the thing on the slide. What does that mean? I should take the 26% times the amount of females in this group, and I find a number. which I have somewhere. Not that difficult, but I think I have it. I get that number to 14.76. If I chose the right one here. I think I did. And then I continue. Then I should find this one would then be E21. And I would take the same proportion now applying to the other thing here. So the same proportion, I should see the same proportion in the other group if the data should match the hypothesis, right? If they match the hypothesis, it's the expected values I'm finding to you here. And then this number becomes, I have to be careful now to make sure I take the right one. I get this at 43.24. Of course, since it should actually match the 58, which it does. And then I do it again. I find also E12 and E22 in the same way. Just they should match the marginals of the table, as you could also say, the totals of the table. Now, here's a rule of thumb that makes it easy for you whenever you see tables like this in the future. Not even a rule of thumb, it's kind of a sort of easy way to remember how to compute expected values without having to think. So that should just keep you aware now. If you don't want to think when you should do expected values in this business here, listen now. So at least put the turn on button now, because here's a trick that could have you not think in the future. I love those rules that can make you not think. Much less stressful than being forced to think. Here's the name of the game. If you see it like this, let's take the E11. If you see it again, it was on the slide also. What was the P? So this is E11 again. P hat. What is P hat? P hat was 58 over 224. And then I say times N1, which was 57, right? So P hat, so E11, and that is the same goes for all of them. All of the expected values come as the product of two numbers divided by the total, 224. And the thing to remember is, when I put myself in this position, the 1-1 position here, I should take the column total times the row total divided by the total, or just the total, right? Row total times column total divided by total. That's the expected values. And that's how you run through all the cells of the table and combine row and column totals by dividing by the total. That's the expected values. I like that. Now, jumping back to my slide where I present the method. Now I combine, as I said, I'm going to compare the observed with the expected in this way, that I take the observed and see how close are they to the expected, right? If the observed and the expected are the same thing, then the data matches the hypothesis, and we should accept, right? The deviation is small, and that is what you can see here. When the observed numbers becomes different from the expected numbers, so if the observed proportions in each group are really different from this joint, from the common proportion, that is that the groups are not the same, then this statistic will start giving a signal, you could say, right? It will start to show some large numbers if the individual proportions are different from the joint proportion, because then the observed number of successes will be very different from the expected number of successes. And then it's not completely, it's seen relative to the expected value. This makes good sense in the way that a deviation of 2 is much more severe if I expect 4, right? An absolute deviation of 2 on the observed and the expected. If I expect 4, it's a 50% deviation, right? If I expect 1,000, then it's not a big deviation to see 998. So I hope you can follow here that it makes good sense to make this a relative thing. To have it like it's really the proportions actually that you compare, not the absolute value. So it has a construction that actually compares the proportions here. Now, another reason for using this particular statistic is that theory can find out how this particular statistic behaves. And now I'm back in track on the sampling thinking, leading to hypothesis testing. Probability theory can tell us that this test statistic, and that's why we name it like that, follows the chi-square distribution that we met last week, where we used it for variances, a completely different situation. But theoretically, it's the same distribution that pops up as the tool to use for hypothesis testing. I mean, theoretically, it's not that surprising because it's really binomial things. Binomials can be approximated by normals. When you square normals, you get chi-square distributions like last time. So theoretically, it makes good sense, even though the situations in the outset are very different. Such a statistic will follow. Of course, it will not be zero. The observed value is not expected to be, or you don't expect the observed values to be exactly the expected values. I mean, that would be odd. So you have to be intelligent about it. You have to realize that you have to accept some sort of difference between the observed and the expected. That is what you will expect, right? Some sort of difference is okay. But what is okay? Well, this is the distribution that tells us the distinction between what is okay and what is extreme. A chi-square distribution is the one to use. The chi-square distribution is the sampling distribution in this case. And if the observed statistic becomes too large, we reject the idea of all the proportions being the same. If it's not too large, we accept, right? That's the same game again. Let's see what happens here. Let's see what the result will be. I'm not gonna by hand sort of continue completely, or maybe should I just do a little? Let's do it. Not like this. Expected. If I do the 4 computations, I already did 2 of them. I could continue. I'm really poor at making these tables here. Oh, that was nice. Expected. 42.24. I do this expected value business, 123.76. And these, the 14.76 and the 43.24, they were the 2 that I computed on the slide before, and here are the other 2. Then I have the observed table. I'm not going to write it again. I'm just going to remember that we have the observed table with the actual numbers. Then I compute the test statistic where I take 4 terms in this test statistic because I have 1, 2, 3, 4 cells of the table. So I have to add a thing for each of those 4 cells. It's a classical mistake to remember to forget 2 of them. We need to put all 4 of them in there to have the theoretical distribution result valid, to have it make sense. Let's take one of these. Let's take the one where the one observed was 23. So let's do this one then. That would be the observed minus the expected squared divided by the expected. That should be in there, right? And then I have similar here, similar here, similar here. I'm not going to spell that out now. For each, I do the same thing. Take the observed, subtract the expected, square it, divide by the expected. And I do it for all 4. Having done that at the end, I get the following statistic, 8.33. So the measure of difference between the observed and the expected, the measure, sort of the difference between the data and the hypothesis that they should be equal, the two disease proportions, is 8.33. The big question is 8.33 a big difference or is it a small difference? So 8.33 is really a measure of the difference between, remember, the two proportions, they were like 40% and 20%. It's the birth control data I'm looking at. It was the 40% in the birth control group, the 21% in the non-birth control group. The 8.33 is a measure of how different these two numbers are, really. It's another measure of the same thing. But is it significant or not? And this is where we should use, did the theory tell us? The theory, I'm jumping back to the theory slide. The theory told us we should use number of group minus 1 degrees of freedom in the chi-square. Question?
Well, if you take the other slide where you do the calculations, because then you have the observed to the right and you put in 23,
Yeah, it should
and
be
you
divided.
divide by 23. Shouldn't it be the exact?
Thank you, DER. Thank you. And very nasty mistake I did there. The other classical mistake, maybe the more classical one. Thank you for, you should have shouted earlier when I do stupid mistakes here. I did the big one. I did the big one. What should we, I think I could, not like this, bugger. We'll do something else. I will do like this, eraser, large eraser. I'll just, maybe I could do it more easily, but now I do it like this, just to make sure. Am I okay, or am I doing new stupid mistakes? I'll take that one when I get there. in 32 seconds. Anyway, let's try again. We take the observed minus the expected squared divided by the expected. Thank you for letting me know that. And then we move on like that. That was an important point. Then the chi-square at the end is 8.33. Is that the one? I mean, this is the chi-square distribution summing up all of these 4 items. Let's check. The R thing here, I'm going to jump the final sort of R thing because we do R through the lectures and I'm not gonna have it detailed part of the syllabus, the R functions for this, but it's just because there are several R functions and you may get confused. So I just decided I'm not gonna hold you up on that, but I'll show them to you anyway. Here is the example. Here's the chi-square test of this proportion, 8.33, which I got from using prop test function. Another function you could use was to use the chi-square function, which is more named like what we do. I do the chi-square test, that's the name of what we do here, the chi-square test. I do it on the box I do it on this 2x2 table of numbers. I put it into a matrix that's a R syntax for having a 2x2 set of numbers. I do the chi-square test on this one, and you can see I get chi-square of 833, and I get a p-value. It's a very small p-value. This p-value is the same that if you found the probability of being to the right of 8.33 with how many degrees of freedom? With 1 degree of freedom, k minus 1, right? You can see this is the p-value that was found by the chi-square test function. So this is how we find p-values. This is to find what is the probability with this chi-square distribution of going beyond the deviation that we have. That's the p-value. So the p-value is 0.0039, 0.004. Have we proven that the risk of the disease is larger in the birth control group than in the non-birth control group? Yes, we have, because the deviation between the two proportions are unlikely large. So we don't believe that they could be the same. We must have proven that the proportions are different, right? That's how we should think here. Good. That was the next to last part.